Welcome to Let's Get to the Marks. This is part 3 of alcohols, organic chemistry A level. Let's get into it. Which statement is correct about both 2-methyl-butan-1-ol and 2-methyl-butan-2-ol? So which is the correct statement? That means that 3 of these are wrong and 1 is correct. So pause the video, have a go, then unpause and watch the answers. All right, I'm going to go through, I know it's a bit long. If you want to forward through to the answer, you can do, but I'm going to go through and explain why each of the wrong answers is wrong. So I'm going to start here at D. They have 4 peaks in their C13 NMR spectra. So, well, if we look at them, for 2 carbons to have the same peak, there's 5 carbons for a start in T-methyl-butanol. So for it to have 4 peaks, 2 of the carbons have to be in identical environments. And there isn't any carbons, or there are not any carbons that are in identical environments. Look, there's 5 different environments just in 2-methyl-butan-1-ol. So, yeah, that can't be right. We don't even need to check 2-methyl-butan-2-ol. Okay, C. They can be formed by the hydration of 2-methyl-butene. Well, let's draw out the formula for 2-methyl-butene. So we need a double bond on the second carbon, and we need a methyl group coming off of the second carbon as well, like so. And what we find is if you hydrate this, the hydroxide group, the alcohol group, is going to add over one of the carbons on the double bond. So it's either going to be that one or that one. Obviously, the double bond's going to disappear. I'm leaving the double bond on here, but that means you're going to be able to make 2-ol or 3-ol. You're not going to be able to make butan-1-ol. So we know that C is definitely wrong, because when you hydrate an alkene, the OH joins onto one of the double bond carbons. Okay, obviously the double bond disappears. Now the B, part B, they can be oxidized by reaction with acidified potassium dichromate. Well, what do we know about this? Well, to be oxidized, you've got to be a primary or secondary alcohol. You can't be a tertiary alcohol. Check out 2-methyl-butan-2-ol, which I've drawn here. It's a tertiary alcohol. Look, there's no hydrogens on the adjacent carbon. If it's a tertiary alcohol, it cannot be oxidized by potassium dichromate. Okay, primary can obviously be oxidized to aldehydes, and secondary can be oxidized to ketones. But here, our tertiary alcohol cannot be oxidized to either. So A has to be the correct answer. They can be formed by alkaline hydrolysis of esters. And yeah, esters can be split to form alcohols. So the answer is yes, esters can be hydrolyzed, and one of the products is an alcohol. Superbulous. Right, guys, make sure you hit the like. There's 2 more questions to get through for this pack, and then I'll finish all of the alcohols on the physics and maths tutor pack. So let's get on to question 11. Okay, question 11. Which alcohol can be oxidized by acidified potassium dichromate 6 but cannot be dehydrated by heating with concentrated sulfuric acid? So what do we know about if you can be acidified, if you can be oxidized by acidified potassium dichromate, you need to be a primary or secondary alcohol, which means the carbon attached to the OH group must have at least one hydrogen attached. So what you want to do is scan A, B, C, and D, see if you can spot a tertiary alcohol, because that definitely cannot be oxidized. So let's find the tertiary alcohol, and C is a tertiary alcohol. 2-methyl-propan-2-ol. It means the hydroxyl group has a methyl group coming off of the same carbon, like here, methyl hydroxyl. There's no hydrogens on the adjacent carbon. It cannot be oxidized because it's a tertiary alcohol. So we definitely know that's wrong. So what this tells us is that A, B, and D are all primary or secondary alcohols, okay? And because they're primary or secondary alcohols, well, actually A looks tertiary as well, doesn't it? I might be wrong there. A does look tertiary as well, because look, it's got 2-ol and 2-methyl. Yeah, so A looks tertiary as well. So A definitely couldn't be oxidized, so that one's out the picture. The answer is actually B when you look at pentan-3-ol and 2,2-dimethyl-propan-1-ol. I'm going to show you why. And both of those, pentan-3-ol and 2,2-dimethyl-propan-1-ol, both of those could be oxidized by acidified potassium dichromate. However, what 2,2-dimethyl propan 1-ol can't have happen to it is it can't get dehydrated, and I'm going to show you why. So it's what have we got here? 2,2-dimethyl propan 1-ol. So when we look at the carbon atom adjacent to the carbon with the hydroxide group on, we will find there is not a hydrogen attached to the adjacent carbon. You're not interested in the carbon. So the one I've circled here in blue, we're not interested in the fact that that's got hydrogens on it. It's these two methyl groups here. They should be a hydrogen instead of a methyl, because you need a pair of electrons from the hydrogen to be donated to form the double bond, to form the alkene, the double bond. Okay, and there's no hydrogen atom on the carbon adjacent to the COH, and so we know that that cannot be dehydrated. So there we go. Let's look at question 12. A group of students wanted to produce a biofuel to power the central heating system in their school. They collected scraps of fruits and vegetables from the kitchens and fermented them with yeast in the absence of air in order to produce ethanol. The aqueous mixture was filtered to remove the remaining solids. The students then set up the apparatus shown in the diagram below and placed the aqueous mixture in a round bottom flask. So we've got apparatus A, B, and C. And let's get on and look at the question. Hopefully you can identify those in your head, what A, B, and C are. There we go. Describe how the students would use this apparatus to collect a sample of ethanol. Include in your answer the functions of the parts of the apparatus. So I'm going to write my answer up here. So we need to include the name of A, B, and C. Well, the first thing you're going to do, you're going to put you've got your stuff in the round bottom flask. So you're going to turn on the heater, normally an electric heater. I know I've drawn a Bunsen burner flame, but that's just being silly. So you're going to turn on your electric heater because you're going to evenly heat the round bottom flask. You want to turn on the water in the Liebig condenser or Liebig condenser at the same time, so that the cooling process can start straight away. Your Liebig condenser is part C. Now, what's going to happen is the water vapor and ethanol is going to evaporate and rise up into the fractionating column, which is A. And so there you go. We've labeled A. It's the fractionating column. And then B is the thermometer. So once we start heating, we want to keep the temperature of the mixture either at or just below the boiling point of ethanol. Of course, ethanol has a lower boiling point than water, so in theory we can get the ethanol off without all of the water evaporating. Of course, you're going to get some water vapor. You're not going to get 100% ethanol with zero water vapor. You're not going to be able to stop some of the water vapor reaching the Liebig condenser, but most of the water vapor, because it's traveling up that column A, is going to condense and fall back into the round bottom flask, whereas the ethanol is going to be at its boiling point. Most of the ethanol vapor is going to go up and travel into that delivery tube into the Liebig condenser. So the water condenses and falls back down into the round bottom flask at A, whereas the ethanol vapor continues on into the Liebig condenser. Only ethanol and maybe a tiny amount of water vapor will enter the Liebig condenser. Now, the Liebig condenser, you already switched the water on at the start. That's C, the Liebig condenser. That is going to have cold water spinning around it, obviously, on the outside. You connect it to an in tap and an out tap, or you connect to an out tube and an in tube, and the in tube is obviously to the tap, and cold water is spinning around it, cooling the walls, and this allows the ethanol vapor to condense, and you collect the ethanol liquid here in the flask. And that's really how to carry that out. So those are all the points you really need to discuss. You should only get minimal amount of water into your distilled ethanol. Coolio. Right, we're going to move on. This should get you all 6 marks. Let's move on to the next part of the question. Okay, for this final question, the student collects a sample of 20 centimeter cubed of liquid and they weigh it. The mass of the liquid sample was 16 grams mass. The density of ethanol is 0.79 grams per centimeter cubed. and water is 1 gram per centimeter cubed. So we know we're going to probably use the density equals mass over volume here. Use the data to calculate the mass of ethanol in the sample collected. You should assume that the volume of the sample is equal to the sum of the volume of water and ethanol. So what they've told us in that last line is that the total volume of the sample is equal to the volume of the ethanol plus some of the volume of the water. So we can set this out and know that this is true according to the facts. The total volume of the sample is equal to the volume of ethanol and the volume of water. Now let's check out our density equation. We don't have the volume of each. We've only got the total volume. So we're going to have to get a bit funky here with the density equation. So we know that 20 centimeter cubed is equal to, what have we been given? We've been given, let's call the mass of the ethanol M. We haven't been given that, but we know mass of the ethanol divided by the density is equal to the volume. So M over 0.79 is equal to the volume of ethanol. So I'm going to represent the volume of ethanol by M divided by 0.79. And that means I can represent the volume of the water as 16 minus M, because the total mass is 16. So we know that if we take away M, the mass of the ethanol, we're left with the mass of the water. 16 minus M divided by 1, which is the density of the water, and that represents the volume of the water. Now we can simplify, because if you divide 16 minus M by 1, you get 16 minus M. So we can get rid of that one, just throw it away. So we have 20 equals M over 0.79 plus 16 minus M. We just need to simplify this. So we're going to times both sides by 0.79. Some people like to do this as like a complex fraction or whatever, but I'm just keeping it as decimals. So we're going to times both sides by 0.79, and I'm going to get 15.8 is equal to M plus 0.79 times 16 is 12.64 minus 0.79 M. Now what I want to do is simplify by adding my m's together. Let's get rid, we've got two different m's. I've got m and I've got 0.7 minus 0.79. Put those together, m and minus 0.79, and I'm left with 15.8 is equal to 0.21 m plus 12.64. Now I need to get rid of that number 12.64. I can do that by minusing it from each side. So take that away and I just got 0.21 on the right, and take it away from the left, the 15.8, and I'm left with 3.16 is equal to 0.21 m. Now I want to find m, divide both, well, sides by 0.21. So I go 3.6 over 0.21 equals m. And if I divide 3.6 by 0.21, m equals 15.04. And you probably just say that m is 15 grams. Don't forget, you can check out the other parts to my alcohol series. All right, guys, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Let's smash the exams.
You're still here? It's over.